2 o'clock. Here we go. Thank you, everyone. If you actually were just at Eric's talk just a second ago, this actually weaves in quite nicely. This talk is going to be about messaging patterns that will make or break your app at scale. Some things that I've seen time and time again, assumptions that were made, myths that were believed that have caused catastrophe when serverless goes into production. So we're going to break that down. But before we do, I'm Jeff Hollan. I guess I'll switch. I think I have an intro slide where I used PowerPoint design suggestions to give us this beautiful slide with the little, like, oh, what's that stupid high school, Saved by the Bell? Like Saved by the Bell themed PowerPoint here. So I'm thrilled to be here in Nashville. I am Jeff Hollan. I'm a product lead on the Azure Functions team. So I'm based out of the Microsoft headquarters in Seattle, working on the engineering team. So my team is in charge of Azure Functions, adding features, shipping it, and servicing it. Before I was on Azure Functions, I was on Azure Logic Apps. And if you don't know what Azure Logic Apps are, I'm not going to talk about them today, but take a note that you should really go and check them out because they are quite useful in a serverless solution. I've been at Microsoft for a number of years now. I was one of the original members of the Azure serverless team when Azure was first saying, like, hey, we want to add some more serverless capabilities. And if you're interested to learn more about my musings of serverless, Twitter is probably where I'm the most active. So we have 50 minutes. I don't even think I'm going to use the full time because I'm just going to cover what we need to cover and go on from there. So here's where I wanted to start. It's kind of posing a question. If you think about serverless, what do you think is the most popular way that people use serverless today? Or even like, what's the most popular trigger? If you're creating an Azure function or an AWS Lambda, what's the most common thing that we see, right? Are they REST APIs, people doing like these HTTP endpoints? I think I will tell you this, for people who are starting, like their first function is almost always something that's HTTP triggered or timer triggered. So is it a REST API? Are they building like these serverless backends? If you think about Jamstack or Netlify or this idea, is it bots? Is it message streaming? Is it backend processing? Like, what is the most popular? And I think sometimes when, and I mentioned when you're getting started with serverless, the most natural thing that people think about is that really simple HTTP endpoint. I'm going to write a little bit of code. I'm going to hit it over the web like an API. It's going to do some work and return back to me a value. Maybe it's a mobile app that's calling it. Maybe it's a website that's calling it. Now, in actuality, this is the usage. I actually literally ran this report last night when I was building this presentation. This is what Azure Functions has looked like in the last 30 days. So there's a couple 100 billion executions in this pie chart. And of all of those executions, about 30% of them are HTTP. But the vast majority are coming from other event sources. And specifically, the two that we're going to talk about today are things like queues and things like event hubs and streams. And then you've got everything else in that little sliver, which are timer triggers and database triggers and storage triggers. But the real meat of the executions are coming from these messaging queues, this asynchronous processing. Now, I can't speak to AWS's data, but I know Chris Munns, one of their advocates, has given a pie chart similar to this in the past, and AWS Lambdas looked very much the same. And part of that, in some cases, is because some of those back-end processing, they just are some massively scalable applications, right? Kind of the 80-20 rule. Even if only 20% of applications are using event hubs, they make up a whole chunk of traffic. So, for example, one use case that I like to share is Best Buy. Best Buy was running on Azure Functions. They shared it some at the Java Spring 1 conference last year before Black Friday, saying, hey, we're now running on Azure Functions for Black Friday. And I was crossing my fingers the entire Thanksgiving holiday, hoping that it went perfect, and it did. They didn't have any hiccups. And so Best Buy had a architecture like the one I'm showing here, and they had a few interesting requirements. They needed to be able to process billions of events, all of these different shipment events, all of these different ordering events. They need to be able to process them behind the scenes. You can see here they have some data that starts on premises in things like Kubernetes that go to the cloud then in things like event streams and event hubs. And I'll talk about AWS service names here in a second. The principles we're going to talk about today span really every cloud. It's just messaging patterns in general. They wanted to make sure that if an error occurs, Kafka, which was the event streaming protocol they were using, they needed to retry it. Like if they were trying to process an order and their code hit an issue, they didn't want to just lose that order. They needed some ability to retry it. And another one that was very important for Best Buy is that ordering had to be preserved. If there was a Jeff made an order, Jeff paid for his order, Jeff asked to refund his order, the order in which those get processed was extremely important, because if I ask for a refund before my payment is processed, it's very different than if I ask for a refund after my payment is processed. And so they were very adamant that, hey, the order in which these events occur has to be preserved. So this is an example of like an asynchronous back-end messaging store architecture. And I'm going to break through and we're going to talk about like, hey, it's these types of applications that make up that pie chart, and what are some things that everybody needs to know in serverless, regardless of your cloud, that will help you be successful in that. So why not use HTTP for everything? HTTP is so easy. I can curl from anywhere. I don't have to learn any new SDKs or APIs. Everybody knows how to talk HTTP. But it has a few limitations. So the first one is synchronous versus async. And again, this is where, if you were in Eric's talk before, he did a fantastic job introducing this concept. Synchronous is the pattern where you call something like HTTP. Let's say I want to get customers. I call the function to get customers. That function says, okay, hold on a second. It talks to a database. It gets the list of customers. And it's like, okay, I have your answer, and it gives it back. And during that whole time, the user is waiting for a response. Asynchronous is more like, hey, generate a report of customers. It immediately returns back a response, does its work, and then gives you the answer later. There's actually an analogy that I really liked with this. Synchronous is like an ATM. Right? Imagine you go to an ATM, everyone needs to do their transaction, they wait in a line, it's very synchronous, it's my turn, I type in my PIN number, I ask for cash, it gives me my cash back. Whereas async is like Starbucks. There's a line, everybody goes up, but they place their order. You don't have to wait for the next person to place their order while they're making my coffee. Right? I place my order, Starbucks says, okay, we'll make your order, I go wait over there, they make my order in the background, and then they call me when it's ready. So HTTP is generally synchronous. So this is one limitation. It's harder to do that Starbucks pattern with HTTP alone. In fact, I don't really even know how you would do it. You really need some state and some messaging behind the scenes to do something async. But obviously, if Starbucks was like an ATM, you'd be waiting forever to place your order. Another one that's tricky with HTTP is guaranteed delivery. I call a website and I say, place this order over HTTP. There's no way to guarantee that the pipes of the internet are going to get the request from my phone to that function, right? Things sometimes are lost in the process. And even if I get a response back, it's very unreliable. It's a single request. It's up to the client to retry. So it can be hard to do that guaranteed delivery. Similarly, retriability and error processing. If I return an error in my function and it's HTTP, I'll get like a 4xx or 5xx response. It's up to the client to retry that request and try again, whereas sometimes I want to be able to retry and handle it on the server side or on the serverless side, I guess I would say. And then ordering is also tricky. Think about that Best Buy scenario. If you send out 10 requests in order, there's no way to guarantee that the pipes of the internet are going to deliver them in that exact order, right? Sometimes things get hung up in some Comcast data center switch. I don't know how the internet works. But things just, you can't rely on ordering. You cannot expect, just because you sent requests in a certain order, that's the order they're going to get received. Now, part of the reason that these problems become even more pronounced in serverless is because serverless is distributed computing. But honestly, serverless is like hyper-distributed computing. And if you're unfamiliar with the term distributed computing, distributed just means that you have multiple machines that are all working towards a shared goal. And I'll show you a demo in a second so you can actually visualize how something like Azure Functions very rapidly distributes. And in order to be successful with distributed computing, first you need to realize that it's happening. You also need to understand a few key messaging patterns. And in fact, where I want to get to in a second is talk about some few messaging myths that are very predominant, thank you, wow, that people get hung up on. So distributed computing is always hard, and serverless makes a lot of things easy, but I think some folks forget about the fact that this is happening behind the scenes. So I just want to illustrate to you this distributed computing concept. I know for many of you this won't be news, but for some of you it might be. And it also gives me a chance to show off some cool stuff. So this is a very simple Azure function. I've written this one in Visual Studio Code. a quick plug for Visual Studio Code and Azure Functions because it's an incredible pairing. So this is just a really simple HTTP function, and I'm doing this because it's easier for me to run this load test. So I could go ahead, I've written my function, I could debug my function, set a breakpoint, do all this great stuff, that's fine. I could now publish this to the cloud. And so I've gone ahead and done that ahead of time. And now that HTTP function is running in the Azure data center. And now I've actually opened up a feature in Azure Functions called the live metric stream. And this gives you a live view into how your code is running in the cloud. And you may notice that right now it's saying my app is offline. It's not actually showing anything. It's showing this big demo chart. That's not my chart. That's saying my app is offline. Now, why is it offline? Well, I published my function, but I never called the thing yet. Or I actually did call it, but it was about 45 minutes ago. So we've gone ahead and scaled any compute that was running my function code down to 0. Right? With Azure Functions, with AWS Lambda, you only pay when your code is actually running, so we don't run your code 24/7. We would lose a lot of money that way. We only run your code on demand. So I could come over here in a different tab, and I could go ahead and trigger this Azure function. And when we come back here to the live metrics view, it takes a little bit of a delay for this to refresh, but we should see here, oh, somebody tried to call Jeff's Azure function. I saw a request, and you'll notice behind the scenes, we have spun up a container. And in fact, this is container 936828855. I'm actually really proud that 936828855 showed up. This is one of our best containers that we have in the entire data center. And it has now shown up for all of you today in Nashville to run my function code. Now, this is serverless, so yes, we have containers and servers behind the scenes. You don't have to worry about them, but I'm just showing you this because it helps illustrate this next point. So I just have one of these online. You notice we actually keep it around. It's not going anywhere right now. We're actually going to keep it floating for about 20 minutes because we assume if you trigger your function once, you're probably going to want to trigger it again, and we don't want to have to keep spinning it up and spinning it down constantly. So right now I have, if you look up right here, one server online. Now what I want to show to illustrate, because this is going to help when we start talking about these messaging patterns, we have 936A2855, and as great as that server is, that container is, it's probably not enough to handle the load I'm about to throw at it. So I'm just going to run this very quick load test, and it's going to throw 1,000 requests a second at this function. And you'll see even before I finish this sentence, in Azure we have detected, oh, there are a lot of requests coming in. This isn't just Jeff hitting this endpoint once. He's now hitting this 1,000 times. And so we are now behind the scenes spinning up a bunch of servers very, very quickly. And so what used to be just one container, now there's 11 containers that are all running, distributing my function executions behind the scenes that happened in just a few seconds to make sure that I had the compute necessary. Now this is really powerful. This is one of the reasons that makes serverless great, is because I didn't do anything to this app to get this behavior. I just published it, and I'm now getting this elastic scale automatically. But the thing I really want you to think about is now there are 11 servers that are all processing 1,000 requests a second distributed across those servers. So I've got some 70 requests a second landing on each container. That means that things sometimes start to act a little bit differently than when I'm just running them on my dev box. If I send 2 HTTP requests in a row, it's very possible that those land on 2 completely different containers. I can't make assumption that this is just one big supercomputer. There's a lot of stuff happening behind the scenes. So that's important to remember as we start going to some of these patterns. So hopefully that made sense. So let's talk about what are your options if you don't use HTTP, if one of those limitations that I listed before is critical. And these are the big 3. This isn't exclusive. There's other trigger types, but really these are the 3 patterns. Even if you use something else, these are kind of the 3 main patterns across the different cloud options. So the first one, you have queues. And this in Azure is something like Azure Service Bus or Azure Storage Queues. In AWS, this is SQS primarily. In the open source world, this is something like RabbitMQ. Another one is topics. I'll define these in a second. Similar kind of a set, SNS here for AWS. And then you have streams, which would in Azure be something like AWS or Azure Event Hubs, AWS Kinesis, or Kafka is the open version of this. So let's drill into each of these, talk about how does this behave when you're at the scale of a serverless app processing millions of events a second, and things that you need to know about that. So we'll start with queues. What is a queue? I don't know how new some of these concepts are, so I won't spend too much time on this. But a queue is pretty simple. you have a client that says, like, I have a message I want to send. It's very much like mailing a letter. I have a letter that I want to send to Josh. I put that letter in a mailbox. It gets to Josh. He opens the letter. Okay? So I'm sending a bunch of letters. They land in your queue, and then I have a consumer that processes it. And if you only have one consumer, it's pretty nice. I know that every message I drop in, that consumer is just going to pull out one at a time, and it's going to process it in order. There's a pattern here called the peak lock pattern, which is when a consumer starts to read a message, it doesn't just pull it and tell the queue, hey, this thing's done. What it actually does is it says, hey, lock this message. I'm working on this message. Don't let anyone else work on this message. Then you have a timeout before the consumer then needs to either respond back with, okay, I finished it and I was successful. That's called completing the message. Like, I'm done with it. You can now remove it from the queue. I processed it. No one else should do it. Sometimes the consumer just dies. Like, what if the OS had to update in the middle of processing it? In that case, after the timeout occurs, the queue's going to stick that thing back onto the queue so somebody else can try it, because you don't want to lose that message. And other times, you might actually be like, you know what, this message is just garbage. No one else should waste their time on it. I'm going to go ahead and dead letter this thing. It means you're going to put it in a special queue that's for like poison messages that you can then go and inspect and process later. So this is all good. You have some guaranteed delivery there. You have a guarantee that at least one consumer will process it successfully somewhere in that process. Now, the thing to note here that we're going to get to in a second is at scale, when you're running across those 11 containers that are all pulling queue messages, each one of those is going to be doing what's called competing consumers. So I have 10 messages in a queue. Consumer 1 might say, okay, I'm going to grab the first 3. Consumer 2 is going to say, okay, I'm going to grab the next 3. And consumer 3 is going to say, I'm going to grab the next 3. This is extremely important to remember when it comes to ordering, because one of the myths we're going to talk about is people assume if you use a queue, the stuff I put is going to get processed in order. But when you have these competing consumers, that's not the case. So before I move on from queue, what is a queue like? A queue is like an airline ticket check-in. There's one really big line of things that need to get checked in, and then you have a bunch of different ticket, like whatever they're called, tellers or whatever else, and they're constantly just saying, okay, the next person, I'm ready. Like, they raise their hand when they're ready. The person who's at the front of the line goes there. Then this person says they're ready. The front of the person goes there. What's nice about this pattern is, like, let's say this person in my slide with those big bags, if they take like 45 minutes to check in, yeah, they're taking 45 minutes of that ticket teller's time, but at least the rest of them are able to keep funneling people, right? So it doesn't really cause many bottlenecks, because even things that are slow and take a lot of time, the other people are able to keep working with them, okay? So more employees, they're all kind of signaling for the next person. A topic I'll go through really quick. A topic is just like a queue, except you have this extra thing called subscriptions, where the same message could actually be received by multiple people. This is more like a newsletter, where I write a newsletter. People who are interested in it subscribe to that newsletter. I just click send once on my newsletter, but it might get delivered to 100 different people. This is the publish and subscribe pattern, or pub/sub. So I have my queue, but in this case, the same message might be delivered to multiple subscriptions, depending on how many people care. So this allows you to make it so that, like, hey, an order was placed in my business, the sales system needs to know an order was placed, the marketing system needs to know the order was placed. I just create one order message, but different systems can pick it up and trigger. Other than that, though, it's very much like a queue. In the same way, too, as I scale out, I might have competing consumers, but they would only be competing per subscription. Okay? For the sake of time, I'll keep moving on. So a topic's very much like a queue, but the same message can be received by multiple subscription groups, a bit like a newsletter. SNS does this in AWS. Azure Service Bus Topics do this in Azure. So the last one, this one's honestly kind of the trickiest, but very useful, is a stream. So this is like Event Hubs, Kinesis, Kafka. And the stream is very different than a queue. You have a bunch of messages that you're publishing, and really the way I like to think of it is it's more like a record player. You have a needle, which is the point in time that you're processing right now. That's that arrow, that reader checkpoint. So all these messages are coming, and you're like, I'm going to put the needle right here at 1 o'clock p.m. on Friday. You can either move that needle forward and keep processing messages forward. You can move that needle backwards, and you could actually process messages in the past. But I'm just progressing one way or the other, and then it's up to something like my function or my Lambda to keep track of where the needle is. There's no per message checkpointing. There's no per message locking in the same way there is with queues. It's really just me keeping track of, okay, I'm on message 600. I'm going to pick up on message 601 and keep moving that needle forward and grabbing groups. Now at scale, this gets a little bit interesting because ordering is extremely important with streams. Streams really care about two things. It cares about high throughput. I want to get a lot of messages processed, and I really care about the order that these things get processed in. So the way they allowed scaling is they have what's called partitions or shards, which says, hey, I'm going to publish a lot of messages, but I'm going to give them a partition ID. So if you think about if it was an order processing system, the partition might be a single customer ID. That would be the key that you would partition on. So all of the events from Jeff go to the same partition. All of the events from Josh go to the same partition. All the events from everyone else go to the same partition. And it makes it so that as your function scales, as you now have 11 of these functions, each consumer can only lock one partition. And it can never have a partition that someone else is reading from. You cannot have competing consumers with a stream in the same way you do with a queue. So I did this lock icon here. In this case, I have 3 partitions or 3 shards. Even if Azure Functions wanted to scale you out to 11, only 3 of those containers are ever going to be active because each one has to lock a partition, and then it says, here's where my needle is, here's where my checkpoint is, and it keeps progressing. So it's okay if that was a little bit confusing if you're not familiar with streams, but I wanted to make it clear because there's some big gotchas here. And if you think about how queues is like that airport counter, streams are a bit more like a grocery store, where if you go to the grocery store and you're ready to check out, there's maybe like 10 lines. You go to a line. In a stream, you're assigned a line. So it's like you go to a line, and now you are in that line. And you have to wait for everybody ahead of you to finish going before you go. So if you choose the wrong line, and it's some old granny who's pulling out all these coupons and taking like 45 minutes, you're waiting. There's nothing that can be done to help you get faster. You are now in that line. And in the stream, you can't change lines like I like to do at Costco, where I'm like, oh, I'm going to go over here. No, you're in that line. Okay? So ordering gets taken care of. You can do a lot of stuff. If those lines are just flying, you can process a whole bunch. But it's important to realize that there is that if you put something slow behind something fast, it's going to have an impact. So now let's address 3 quick myths, and then we'll wrap up. So this is my favorite myth of serverless, and I see so many people get hung up on this. I can build a system that will allow me to process a message once and only once in serverless. And it sounds like the thing everyone wants to do. I'm placing an order. That order means it's going to charge my credit card. I do not want to charge my credit card twice. If Jeff makes the call to say charge my credit card, I only ever want to call the credit card API one time. I don't want to call it twice. And so they think, you know what, I'm going to use something like a queue, and I'm going to do something like just complete it right away, and then I will only ever receive it once. And I will tell you right now, in distributed computing, I don't care what marketing page you have found, you cannot do this. Don't try it. You cannot. And if somebody thinks you can do this, I want you to come talk to me afterwards. Because there are a few messaging systems that are like, we can do this. And it's like, not really. Because once you start to look at like a real scenario where your compute is running over here and your data is running over here and your credit card system is running over there, it just falls apart. And that's what distributed computing is. So imagine like a flow like this. Your function triggers on a message. The next step in the code is it validates the message. The next step in the code is it calls the payment API. And the next step in the code is it completes the message. Think about every gap between those things. What happens if my function fails right then? What if the container just erupts into flame? The whole data center just disappears. Okay? So even if a message thing might say like, no, we have a way for you to say no. After step 1, we won't let anyone receive that message again. But what if all of a sudden that container just vanished right there? You would never call the payment API. You never charge the customer. Nothing ever happened. But the inverse might happen. What if you call the payment API and then something terrible happens? It's very possible that I mentioned before, your message thing is going to be like, well, this function just died. I'm going to reprocess it again, and it's going to start again at step 1. So failures can happen at any single point during an execution. There is no rhyme or reason. As Eric mentioned in the previous one, you have to build everything with the assumption that you fail. So you have to understand with messaging things, it is at least once guarantees. You are guaranteed that at least once, all 4 of these steps will happen but it may happen more than once. Hopefully it doesn't, but it may. So don't try to build a system where you think that you can. Now, there are ways around this. The big word here is idempotent. It's a very weird word that took me a long time to understand even how to pronounce. I hope I got it right. And this just means you could run the same code. You could run those same 4 steps with the same input, and it wouldn't create multiple versions of consequences. Meaning, I create a request which is charge Jeff's credit card $50 for this shirt. If I make that request 10 times, it's not going to charge my credit card 10 times. It's only going to charge it once, and the other 9 times, it's going to have logic to let it know what to do. So the things you should be aware of here is use IDs wherever possible. If I'm not just charging Jeff's credit card, but I'm charging Jeff's credit card for transaction 123, and then when I call Stripe, which is like a payment API, Stripe has a way to say this is a transaction ID, and I say, hey Stripe, will you charge Jeff's credit card for transaction 123? Stripe can return back and say, hey, I already charged Jeff's credit card for ID 123. And your storage database can say, I already have a document for ID 123, or I have this event ID already. You've got to use these IDs so that your systems know, did I already do event ID 123? So just be aware of it. Don't think you can do once and only once. I wish we could. It'd be a lot easier, but we can't because distributed computing, it's fun. It's fun for everyone. Okay, second big myth that I see, and I kind of teased this one a lot already. Using a queue means that my messages are going to be processed in order. Because a queue, right? No one cuts in line. I'm going to get processed in order. But again, if you think about this scenario here, where you have these competing consumers, the queue might be saying, I have A, B, C, D, E, F, G. And consumer 1 says, I'm going to take A, B. And then consumer 2 says, I'm going to take E, F. And consumer 3 takes, I'm going to take C, D. It's very possible that each of these finish in different times. And so the actual order that things get processed is more like A, E, D, C, B, F. I might have lost a letter there, but you get the idea. So this may backfire to you once your app starts to scale because things start processing competing in different orders. Now for this one, there are ways around this too. 2 very important strategies that work. In Azure Service Bus, there's a feature called Sessions, which means these events need to be processed in order. They are part of the same session. In AWS, SQS has first in, first out queues, and you set something called a message group, or you can use a stream. Both of those will give you ordering. They have pros and cons, but you can do it. Ordering is an important thing, but an example of what a session might look like, I might have 2 sessions. One is called my number session, the other is called my letter session, and we will make sure that a consumer says, I'm interested, I'll take the letter messages, and it will take all of those messages and process them in order. Now, the final myth that I want to talk about is this one, which is using a stream guarantees me high throughput. Hey, if I use something like Kinesis, if I use something like Event Hubs, I'm automatically going to get a massive amount of requests processed every second. And that is not the case for a number of reasons. The first one I talked about is that imagine that these are 3 partitions. If I have really long processing messages in a partition, then it's going to have to wait for other things in that partition to happen. So if you have high variability of task sizes, oftentimes a queue is better. Because a queue, you can say, hey, I'll take the next person, I will take the next person. Whereas in Event Hubs, you're stuck in that checkout line. The other big thing here with streams that's important to note is the amount of partitions, the amount of shards that you select is extremely important. If you create an Event Hub and you say, I only want 1 partition, you're only ever going to get one of those containers to process it at one time. So you bottleneck your system. So you want to crank that number up as high as you can. Because if you set it too low, it's going to limit how many things your Lambda can lock. Right? Same for Kinesis with shards. You need to be aware that it's not just because you're using a stream you get high throughput. You need to make sure that you're partitioning correctly, that you're load balancing across your partitions. If you choose a bad partition key, like if you choose a partition key for customers and you're going to partition your customer data based on customers who are alive and customers who are dead, you're probably going to get all of your customer data landing into the I'm alive column unless you're a really shady business, and then maybe it's split between the 2. But you got to choose a partition key where it's going to be evenly distributed. All right, we're about wrapping up. So key takeaways. We will wrap up. Wow, very early. I had more I was going to talk about, but this is fine. Some key takeaways, and we'll have an extended break. The big stuff I want everyone to know, don't use HTTP for everything. It's a bad choice for some problems. It's great for some, If you want synchronous, if this is going to be called from a web browser, HTTP is fantastic, but there are often problems where you're going to be better off doing asynchronous, where you're going to be better off with guarantees around when messages can be delivered and guarantees around ordering. But you need to figure out what are the characteristics that are most important for the app that you're building. Do you really care about transactional retries? Do you want to make sure that every single message can be individually retried and tested again? If so, maybe something like a queue is the best fit. If you really care about massive throughput, you want 100,000 messages every second, you're probably going to get that from streams, because streams can just move that needle really, really fast, whereas queues, it's doing like this individual checkpointing for every message. Do you have high variability in tasks? Do some tasks take a long time, some tasks are very short? Then a queue is probably the right one. Does ordering matter? Well, then you need to make sure you're using sessions or you're using streams. So think about what are the characteristics that are most important, and then choose the messaging platform as appropriate. If you choose the wrong one, you're going to be in a world of hurt. And consider the trade-offs. I mean, it's hard, but this is engineering, and engineering is all about making the trade-offs. These are the resources that we have. This is the problem that we're set to solve. We're going to have to make some compromises, right? We don't get infinite budget and infinite time, and we don't have technology that's purpose-suited for exactly what we're doing. That's what makes our jobs fun. We have to go solve problems. We have to go build new things. So consider the trade-offs. Consider what's going to be the best choice, and then move forward with it and iterate and continue to adapt and evolve. So that's it. I know that's a little bit early, but I'm going to cut anyway because I don't want to just drag on. There was a little bit more where we could talk about things like exponential backoffs and circuit breakers and error handling, but I think I'm okay. This was enough. This was deep enough. So with that, thank you all very much. Hopefully that was helpful. Hopefully that made sense. As I mentioned, these patterns apply to whatever cloud provider you're using. And with that, with the extra time, you can go ahead and check out the vendor booths or come up and ask me if you have any other questions. So thanks a ton.